is calculated with an error of less than 4 centimeters. Think about that. We have a circumference of 125 billion kilometers and the margin of error is less than the length of your little finger. We can study the problem using the example of the Earth. The diameter at the equator is 12,756 kilometers. The circumference of the equator is 40,075 kilometers, which is the distance you'd have to cover if you want to travel around the world, not taking into account mountains, valleys and obstacles, like buildings, parking lots, ocean waves, etc. How wrong is your odometer when using it? Rounded off value of pi. Its error is about the size of a molecule. Naturally, there are different kinds of molecules which do differ in size, but you get the idea. The size of the error is about 10,000 times less than the thickness of a strand of hair. Now let's take the largest possible object, the visible universe. Its radius is approximately 46 billion light-years. How many decimal places of pi do you need to use to calculate the circumference of the universe with an error of no more than the diameter of a hydrogen atom, the smallest atom? You need 39 places following the decimal. If you think about how huge the universe is, well and truly larger than we could ever comprehend in such a tiny atom of hydrogen, you will then understand that a really accurate calculation doesn't require very many decimal places of pi. There is an abundance of surprising facts about this. Constant Stanislaw Ulam, a Polish-American mathematician, in 1965, rolled the numbers of pi out on graph paper. He put the 3 in the center, and moving in a counterclockwise spiral, wrote down the numbers after the decimal point in addition. He drew circles around all the prime number. He was both surprised and aghast when he noticed that the circles were organized in straight lines. Then, using a special algorithm, the mathematician made a color picture. Based on this drawing, which is called the Coulomb spiral, seemed that pi correlates a curved object circle with a straight object. We can find it in all sorts of places. Some find the number pi in riverbeds, the length of a river, with all of its meandering bands in relation to the straight line between its source and its delta. According to calculations, is on average pi models for virtually all wave-related phenomena. Will involve the number pi. Let's take light and sound, for example. Pi determines what colors are visible in the spectrum of a rainbow and how the notes C should sound. The number pi is also observed in the process of the cells in apples acquiring a spherical form, and in the brightness of the light output of a supernova. Well, perhaps the code of the universe is encrypted in this number. One of the moons of Jupiter, known as Io, played a significant role in the advancement of 17th-century astronomy. Studies have shown that in the process of crustal compression, about 100 mountains were formed on the surface, changing the landscape over the next number of centuries. The peaks of some of these, for example S. Brusselmans, exceed the height of Mount Everest twice over. Along these same lines, there are vast plains on the surface of this satellite. Its surface has unique properties and comprises an abundance of colors: white, red, black, green and even orange. This distinctive characteristic is due to regular lava flows, which can stretch up to 500 kilometers. The high density indicates that there is virtually no water on this satellite, although there have been small pockets of water accumulation found. This deficiency of water is likely due to the fact that during the formation of the Solar System, Jupiter was hot enough for volatile substances such as water to evaporate from Io's surrounding vicinity, although not hot enough for this to happen on the more distant satellites correspondingly. Often found on the satellite surface are volcanic depressions just like in humans. Although they are called battery, they are characterized by an even floor. In steep walls they very much resemble terrestrial calderas. However, it is still unknown whether they were formed by the collapse of the magma chamber and the collapse of the top of the volcano, like their terrestrial counterparts. Unlike similar geostructures on Earth and Mars, volcanic depressions on Io generally do not lie on top of shield volcanoes and are usually larger, with an average diameter of about 41 kilometers, and the largest Loki Patera is 202 kilometers in diameter. It is remarkable, but battery often serve as sources of volcanic eruptions or fast-spreading lava flows, as in the case of an eruption in the Jishbar Patra. Or they themselves filled with lava, becoming lava lakes. The lava lakes on Io are covered by a lava crust, which crumbles away and renews continuously. Image analysis has shown that the lava flows on Io are primarily composed of molten sulfur. However, subsequent ground-based infrared observations indicate that the flows are in fact composed mainly of basaltic lava and ultra-basic rock. An outstanding representative is Musubi, an active volcano on this moon of Jupiter, which is located on Io's leading hemisphere in the Taurus region. The volcano is noteworthy for one of the largest lava flows, both in Ohio and in the entire Solar System, covering an area of 240 kilometers. Despite the extensive volcanism that characterizes Io's appearance, most of its mountains are not volcanic in origin. The majority of them are formed as a result of compressive stresses in the lithosphere, which lift and often tilt portions of the satellite's crust, thrusting them over each other, much like giant ice flows. This is precisely why virtually all of the mountains of Io are at some stage of destruction, with large landslides being widespread at their bases. Of course, it appears that caverns are the main factor in the destruction of mountains. Believe it or not, but this tiny cheese ball Io plays an important role in shaping the magnetic field of the giant planets. Jupiter, the magnetosphere of Jupiter, absorbs gases and dust from the thin atmosphere of the satellite with a speed of 1 ton per second. All this matter, depending on its composition and degree of ionization, ends up in the various neutral clouds and radiation belts of Jupiter's magnetic sphere, and sometimes even escape Jupiter's system altogether. Also interesting is the fact that Io's moon is surrounded by a so-called atomic cloud of sulfur, oxygen, sodium and potassium, which extends to a distance from its surface equal to about 6 times its radius. These particles come from the upper atmosphere of the saddle, and they are activated by collisions with particles from the plasma tours and other processes in Io's Hill sphere, where its gravitational strength exceeds that of Jupiter. Io's orbit run its scores within the radiation belt known as the plasma tourist's Adinet-shaped ring of ionized sulfur, oxygen, sodium and chlorine. The plasma in it is formed from the neutral atoms of the cloud surrounding Io, which is ionized and carried away by Jupiter's magnetic sphere. It's not hard to guess that Io is not at all like most satellites of the gas planets, which contain huge masses of ice, as it consists mainly of silicates in Iran. Like the inner planets, further still, its interior is also incredibly active. Modeling of Io's internal composition shows that at least 75% of the mantle consists of the magnesium-rich mineral forsterite, a composition similar to that of alchondrite meteorites. It is obvious that the ratio of the concentrations of iron and silicon there is higher than those on the Moon. For the Earth, but lower than on Mars, the latest research has shown the presence of an induced magnetic field on Io. For each, an ocean of magma with a depth of 50 kilometers would be required. This layer is estimated to be 48 kilometers thick. It makes about 10% of Io's mantle, and its temperature reaches about 1,200 degrees Celsius. It is not known whether this 15% melting is compatible with the conditions of significant amounts of molten silicates in this inconceivable ocean of magma. Io is a bright and wondrous world which has no equivalent in the entire solar system. Active volcanism on a satellite the size of our Moon is absolutely astounding. And the pioneering photographs of the satellite surface, which have been obtained by a number of spacecraft, compel us to plunge again and again into the atmosphere of this distant and mysterious world.